Deep in the constellation Libra, about 200 light-years from Earth, lurks one of astronomy's most perplexing mysteries. A star officially catalogued as HD 420283 has earned the nickname Methuselah, for good reason. When astronomers first calculated its age, they discovered something that shouldn't exist. This ancient celestial body appeared to be older than the universe itself. The discovery sent shockwaves through the astronomical community. How could any star predate the Big Bang? The initial measurements suggested Methuselah was approximately 16 billion years old, while our best estimates place the universe's age at 13.8 billion years. This created what scientists call the Methuselah paradox, a contradiction that challenged our fundamental understanding of cosmic chronology. To comprehend the significance of this discovery, we must first understand what makes Methuselah so extraordinary. This star belongs to a rare category known as population 2 stars, ancient remnants from the early universe. Unlike our Sun, which contains abundant heavy elements forged in previous stellar generations, Methuselah has extremely low metallicity. In astronomical terms, metallicity refers to elements heavier than hydrogen and helium. Methuselah's composition consists almost entirely of these primordial elements, indicating it formed when the universe was still in its infancy. The star's chemical fingerprint tells a remarkable story. During the first few 100 million years after the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. The first generation of stars, called population 3 stars, lived fast and died young in spectacular supernovae, scattering heavier elements throughout space. Methuselah formed from material slightly enriched by these cosmic furnaces, making it a second-generation star that witnessed the universe's chemical evolution. What makes Methuselah even more intriguing is its behavior. The star moves through our galaxy at an unusually high velocity, traveling at approximately 1.3 million kilometers per hour, relative to our solar system. This rapid motion, combined with its ancient age and unique composition, suggests a fascinating possibility. Could Methuselah have originated outside the Milky Way galaxy entirely? The traditional explanation for the age paradox focused on measurement uncertainties. Determining stellar ages requires precise calculations based on luminosity, temperature, composition, and complex stellar evolution models. Each measurement carries inherent uncertainties that compound when calculating age. Recent observations using the Hubble Space Telescope and improved theoretical models have refined Methuselah's age estimate to between 12 and 14.5 billion years, with uncertainties of approximately 800 million years. These refined measurements technically resolve the paradox by bringing the star's age within the realm of possibility given the universe's age. However, a revolutionary theory suggests an entirely different explanation for Methuselah's apparent antiquity. This hypothesis involves one of Einstein's most profound insights: the relationship between gravity, space, time, and motion described in his theory of relativity. Einstein's general relativity reveals that time is not absolute, but relative, affected by gravitational fields and velocity. In regions of intense gravity, such as near black holes, time dilation becomes extreme. An observer near a black hole's event horizon would experience time passing much more slowly compared to someone in normal space. From the perspective of a distant observer, time appears to nearly stop at the event horizon itself. Conversely, in regions of extremely low gravitational influence, time should theoretically pass more quickly relative to areas of higher gravitational density. The challenge is that such regions typically lack observable objects, making direct measurement of this effect nearly impossible. The vast cosmic voids between galaxy clusters represent some of the most gravitationally sparse regions in the universe, but they contain virtually no stars or galaxies to serve as natural clocks. This brings us to the innovative hypothesis that could resolve the Methuselah paradox. What if this ancient star didn't form within the Milky Way, but instead traveled through the universe's largest structures, experiencing different rates of time passage during its cosmic journey? The universe exhibits a remarkable large-scale structure, often called the cosmic web. This three-dimensional network consists of dense filaments of dark matter and galaxies connected by thin strands with enormous voids between them. These cosmic voids, some spanning hundreds of millions of light-years, contain very little matter and consequently have extremely weak gravitational fields. Consider this scenario. Methuselah formed in the early universe, roughly 13 billion years ago, in a region that would later become part of a cosmic void or the outskirts of a galaxy cluster. As the universe expanded and evolved, gravitational forces ejected the star from its birth environment, sending it on an epic journey through space. During this journey, Methuselah would have traversed regions of vastly different gravitational environments. While passing through dense galaxy clusters, the star would experience stronger gravitational fields where time passes more slowly. Conversely, during its journey through cosmic voids and intergalactic space, where matter density approaches near vacuum conditions, time would pass more quickly, relative to our galaxy-bound perspective. The cumulative effect of this temporal variation could be profound. If Methuselah spent significant portions of its existence in low-density regions, where time passes more rapidly, it could have effectively aged more than the universe as measured from our perspective within the Milky Way's gravitational environment. This hypothesis gains credibility when we consider Methuselah's current properties. The star's high velocity and trajectory suggest it's not gravitationally bound to our galaxy in the same way as typical Milky Way stars. Instead, It appears to be passing through our galactic neighborhood, possibly as an intergalactic wanderer that has spent eons traveling between galaxies. Furthermore, the star's low metallicity supports this extragalactic origin theory. Stars that formed in the early universe within regions that later became cosmic voids would have had limited exposure to the heavy elements produced by subsequent generations of stars. This isolation would preserve their primordial composition, exactly matching Methuselah's observed characteristics. The implications of this theory extend far beyond solving a single astronomical puzzle. If confirmed, it would provide direct observational evidence of time dilation effects on cosmic scales, validating Einstein's predictions in environments previously impossible to test. It would also offer insights into the early universe's structure formation and the complex dynamics of intergalactic star formation. Moreover, this hypothesis suggests that other apparently paradoxical objects might exist throughout the universe. Ancient stars that spent their lives wandering through cosmic voids could appear older than the universe when measured by our local standards. These cosmic time travelers would serve as living fossils, carrying information about conditions in the early universe while having experienced time differently than objects confined to galactic environments. The verification of this theory requires sophisticated observational campaigns and theoretical modeling. Astronomers need to precisely map Methuselah's trajectory through space, working backward to determine its possible origins. Computer simulations must model the star's journey through varying gravitational environments, calculating the cumulative time dilation effects over billions of years. Advanced spectroscopic analysis could reveal additional clues about the star's history. By studying the minute traces of heavy elements in Methuselah's atmosphere, scientists might determine when and where the star encountered enriched material during its cosmic voyage. This forensic astronomy could reconstruct the star's path through the evolving universe.